So what we did on Friday was we kind of like started getting into actual calculus, and they even gave some meaning behind that difference quotient thing that that limit definition of the difference quotient thing that I've been giving to you for since almost day one in this class probably. Okay, and you even saw in pre-calculus some, right? Now there's some actual meaning behind it. Okay, so calculus, part of the development of calculus was a result of trying to solve what was known as the tangent line problem, okay? And so what that means is scientists, I guess, wanted to come up with a way to describe the rate of change of a curve at an instant, right? So not trying to come up with some average rate of change, but come up with the rate of change of a curve at an instant. They could come up with the average rate of change, no problem, right? An average rate of change is just a matter of finding the slope between 2 points. Right, and so that's essentially like, you find the slope of the line. We know how to find the slope. You guys know that since Algebra 1, just use slope formula, y2 minus y1 over x minus x1. But how could we use, what they were able to, not how could we use, but what they were able to do then was take that slope formula that we know, okay, and use limits to then create a tangent slope, the slope of a curve at a point, okay? And so we start with what we know, right? Here's our curve f. And so we can use 2 points on f, okay, defined in a very specific way. We're using 2 points in a very basic sense. We just use 2 points and use a slope formula, y2 minus y1 over x2 minus x1. The way we define those 2 points, though, we start with a generic point c, and then that would give it the y-coordinate f of c, right? And then we go from that generic x-coordinate of c, we go out some distance delta x, okay? Delta just means change in x, so it's a small change in x, which then takes us to a new x-coordinate, c plus that delta x, right? That's our new coordinate, right? We started at c, we add the delta x to it, and now this coordinate c delta x. And then so its y-coordinate would be f of c plus delta x. So those are your kind of 2 points there, okay? The slope of this line, using these 2 points, okay, it's not a tangent line, it's a secant line because it hits 2 points. And it's known as like an average slope or the average rate of change of f. I should probably put an of f in there, right, to help out. Okay, that's the average rate of change because it's just like the regular old slope formula between those 2 points. When we plug those points in, right, to our slope formula, some slight simplification yields something very familiar to us. F of c plus delta x minus f of c all over delta x, right? That's like that difference quotient, right? Difference quotient because, well, difference, there's subtraction, but quotient because there's also division. So it's a difference quotient, okay? Not that profound. Mathematicians are not very creative sometimes in their naming, okay? It's like, subtraction and division. Let's call it difference quotient, okay? But how can we use this, though? This is still a secant line. How can we use this to create a tangent line? To create the slope of a tangent line, or find the slope of a tangent line, right? We have 2 points. How can you find the slope of just 1 point? Well, it all deals with how we kind of set this up. So the idea here, if we wanted to find the slope at a single point instead of 2, we have here another curve, okay, now a more realistic looking curve here. That's like a parabola, right? And we want to find the slope here at this point. And so what we can do, for example, what we did here is we found the slope between these 2 points on our curve, and then we moved this point closer, keeping this point the same, and we got, the slope between those 2 points. Okay, and we can see that while this slope was the slope of 0, when we move that point closer, the closer this point gets to, this one, we get more and more close to approximating what this tangent slope is going to be. Right? We already have an intuitive sense that at this point the slope is going to be negative. Okay, and so when we do the slope between these 2 points, we have a zero slope. And we're like, that's probably not very good. But as we get this point, move this point closer, now we have a negative slope, and it's more close to what that tangent slope is going to be. But the problem is, our regular old slope formula doesn't quite work with the normal way that we use it to find that slope. However, we go back to what we were talking about before. If we can diminish this delta x, if we can diminish it so much that it brings this point in almost right next to this point, well, then we basically get what's essentially going to be that tangent slope there. We just diminish this delta x, and then that brings this point in closer and closer and closer and closer, and approximates that slope right there to be exactly what the tangent slope would be. So how do we diminish delta x? What concept are we going to use? Well, we'll just use the limit. the limit as delta x approaches 0. That's going to shrink the distance between these 2 points, bringing in that c plus delta x towards the c, and by bringing in that point, my secant slope is now going to become closer and closer and closer, approximated to the tangent slope at that point. Okay, and that's the idea. Okay, so that is the meaning behind taking the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. It finds the slope of the tangent line at a specific point. Okay, there's a little bit of a definition here. Okay, and then I just threw in some extra phrases, right? The slope of the tangent line to the graph of f at the point cf of c is also called the slope of the graph of f at x equals c. So the tangent slope and the slope of the graph of f, same thing, right? And also sometimes we call that the instantaneous slope. Why is it called instantaneous? Well, what do you think? It's happening at a point, okay? It's an instant. It's happening at a single point, so it's an instant, okay? Or it's the instantaneous rate of change also, because again, what is the slope but just the rate of change of something? So all these are synonyms for the same idea. Slope of the tangent line to f, slope of the graph of f, instantaneous slope of f, or instantaneous rate of change of f. All those things mean the same thing, okay? They mean finding the slope of the tangent line of f. Okay, so let's then scoot on to the next page where we're actually going to do some real work, some actual application. Excuse me, and not just conceptual stuff. Okay, so let's put this into play. So now for this first one, example 1, here's an actual problem. We want to find the slope of the graph of f of x equal to 3x minus 1 at the point 2, 5. Okay, so to find the slope here, let me find where my notes are. Yeah. Okay. To find the slope here, we're going to use the limit. We're going to put this limit into practice and see if it actually works. See if we can get something from it. Okay. Now I've got c's in here. Normally, in place of the c's, we see x's, and I'll explain, what the x's, the purpose of those x's here in a second. Okay, or why we use x's generally and not c's. But for now, we're going to use the c. Okay, because remember that c is it's specifically referring to the slope of the graph at the point x equals c. Right. So we want to. This is we use the c when we're trying to find the slope at a specific point. So at what specific point are we trying to find the slope of the graph? 2, 5, right? But we don't plug in the entire point 2, 5 here. C is an x value, so it's going to be 2. That is our c value there. Okay, so I'm going to rewrite this then as the limit as delta x approaches 0. Again, we're evaluating here at x at c equals 2. And instead of writing f of c plus delta x, we're going to write f of 2, because c is 2, right? So it's 2 plus delta x minus f of 2 all over delta x. Okay, so let's continue simplifying here. So this will be then the limit as delta x approaches 0. Because right now, if I plugged in 0, I'd still get 0 over 0. So we have to do some simplification. So f of 2 plus delta x. Well, here's f of x. Right, it's 3 times x minus 1. So f of 2 plus delta x, how can we write that out? Well, if f of x is 3x minus 1, then f of 2 plus delta x, it's going to be 3 times parentheses, right, 2 plus delta x minus 1, right? The 2 plus delta x plugs in for where the x was. Okay? Minus f of 2. Okay, so I'm going to put parentheses around this, minus the quantity f of 2. So f of 2 is going to be 3 times 2 minus 1. All over delta x. Okay? So again, it's our normal kind of substitutions. This first f has a delta x in it, so wherever we see the x, it's going to be 2 plus delta x. That's why it's 3 times 2 plus delta x minus 1. And the second f just has 2, so wherever we had an x, now it's going to be 2. So it's 3 times 2 minus 1. Okay? If it asks for, f of Bob, it would be 3 times Bob minus 1, right? It's just whatever is in place of parentheses there, that's what gets plugged in for the x. Okay, so let's see here. That's going to be we still haven't evaluated the limit yet. And now let's simplify. So let's see here. The 3 distributes, right? So it's 6 plus 3 delta x minus 1. And then let's see here. I'm going to do some math. So 3 times 2 is 6. Minus 1 is 5. So it's going to be minus 5 all over delta x. Okay. And then does this simplify at all?
Oh, yeah.
Oh, yeah. So what happens?
The constants on the top.
Yeah, so 6 and minus 1 and minus 5, they cancel out, right, and just leave a 0. And so we're left with the limit as delta x approaches 0 of 3 delta x over delta x. And then how does that simplify? The delta x's cancel, and so I have the limit as delta x approaches 0 of 3.
No, never mind.
So what is the limit as delta x approaches 0 of 3? There's no delta x's here to plug the 0 into, so what's this equal?
3.
Just 3, yeah. There's no place to plug in that 0, so the answer is 3. Whoa! All that work, Mr. Whitmire, to get some stupid little answer, 3. Why does this answer make... Oh, go ahead, Anna, first. Question.
Do you have to write it like limit and then delta x approaches 0 equals 3?
Like, did you want to just like have it just 3 right here and not the limit is delta x approaches? That's fine. Yeah, that's fine. Why does this answer make sense? Why does it make sense that the slope of the graph of f of x equals 3x minus 1 has a slope of 3 at 2? Yes.
Because the original graph of f of x is just a straight line with a slope of 3.
Right.
So
exactly right.
When it passes through 2, 5,
so at the point 2, 5, the slope should still be 3. Exactly right. So let's not try to miss out. Sometimes people can't see the forest for the trees, right? So I mean, it's like the answer was always right in front of us for this one about what our slope was going to be. This is the equation of a straight line, and it's in slope-intercept form. The slope of this line is 3. Does the slope of a line ever change? No. So at any point along my line, at any point I pick, okay, I had better end up with a slope of 3 at an instant. At any instant along my line, my slope should be 3. So this should not surprise us. Okay, the slope of the line is 3 for any x value. Okay, the slope of the line is 3 for any x value. Okay, and I left some space to graph that. I'm not going to bother with graphing this one because it's kind of, I don't know, it's a line, right? We know how to graph a line. I think it's not going to be too necessary for this one. The next one we will graph, though, for sure. Okay? This one, it's pretty obvious, right? If your line has a slope of 3, then no matter where you are on that line, the slope at that instant will also be 3. Okay? The average slope, so if I pick 2 points on my line, what will the slope between those 2 points be? 3 as well, right? So the average slope and the instantaneous slope will always be the same for a line because the line slope never changes. Okay? But what if we don't have a line? Can we still find the slope of something? Like a curve? And the answer is yes. This is more powerful than just finding the slopes of a line. We can also find the instantaneous slope or the instantaneous rate of change on a curve. So let's graph x squared plus 1, which we all hopefully should be fairly familiar with, because that is one of our kind of like function families we should be familiar with, the x squared. And the plus 1 means we're going to take that parabola and do what with it? Yeah, shift it up 1, up 1. Okay, it's when the plus or minus 1 it's when the plus or minus 1 is inside parentheses that you then shift it left or right. And the way I remember that, okay, is that it's with the x, right? If the number's inside, kind of with the x, then that shifts it left or right. If the number's kind of on the outside, then that's like affecting the y. Okay, so let's graph this here. So let's see. So that means at the point 0, we should have y value of 1. let's see, at 1, 1 squared is 1, plus 1 is 2, so at 1, 2. And then also, by symmetry, negative 1, 2 as well. And then 2 squared is 4, plus 1 is 5, so 2, 1, 2, 3, 4, 5. And then also, by symmetry, negative 2, 5 as well. Okay, and then we'll just kind of like... and this is the function f of x equals x squared plus 1. We should have the x coordinate and the y coordinate. Okay. Now, it says here that we're going to find the slopes of the tangent lines, that is, find the derivative, that is, find the instantaneous rate of change, that is, find the slope of f, here in this case, x squared plus 1, at the points 0, 1, and negative 1, 2. So those are, we're going to do two different problems here, two separate problems, okay? And we're going to do the 0, 1 first, okay? So we'll do at 0, 1 first, the slope at 0, 1. That's the first one we'll do. So now, look at the point 0, 1 on your graph of f. Just look at that point, okay? You already, as mathematical students, have an intuitive sense about what the slope should probably be at 0, 1. Okay? What do you think it should be?
0.
0. Why?
Because
It's a shallow part of a problem.
where it is.
It kind of bottoms out there, right? It's not really decreasing. It's not really increasing. It's kind of just flattening out right there. For that instant, it's flattening out. And then to the right, what type of slopes do we expect? Positive slopes. And then to the left, what type of slopes do we expect? Negative slopes. Exactly right. So you already have an intuitive sense of what this slope will probably be. At this instant, we want to believe the slope's going to be a 0 slope. But let's actually do the math and see if it backs it up. Backs up our intuitive sense. All right, so let's set this up. So it's going to be the limit as delta x approaches 0. And what is our c value this time? Yeah, it's the x value of 0, right? Where 0 is our point. We don't need to worry about the y coordinate. Okay, in this case, it's just the x. So 0 plus delta x minus f of 0 all over delta x. Now, some of you might be looking at this and saying, Mr. Widmeyer, 0 plus delta x, could we just write delta x here? And the answer is, yeah, if you want to, absolutely. Feel free to simplify that inside. We couldn't do that earlier, right, because it was 2 plus delta x. And 2 plus delta x, that doesn't really simplify. But 0 plus delta x, absolutely, we can go ahead and do that. So you can write just f of delta x minus f of 0 all over delta x. Okay. So if f of x is x squared plus 1, then f of delta x is going to become what?
Delta x squared.
Delta x squared. Plus 1, right? And then minus the quantity. So now f of 0. Well, so 0 squared is 0, plus 1 is 1, so it's just going to be minus the quantity 1 there. All over delta x. Okay. So there's our setup. Questions so far? Did I lose anybody yet? No questions so far? Okay. Now we simplify, right? What can cancel here? The 1s. So we're left with delta x squared over delta x, which simplifies to what?
Delta x.
Just delta x. Well, I think we've lost Caleb. There he is. He's back.
Don't go towards the light.
That's right. Don't go towards light, Caleb. Okay. And what's our final answer then? What do you know? You're all right. The slope is 0.
Never would have guessed that one.
Okay.
Now we gotta go to negative.
Right. So how about you guys now try it? Let's find the slope at negative 1, 2. Again, you may not be able to tell exactly what the slope number is going to be, but we all hopefully can see that the sign of the slope should be what? It should be a positive or negative slope here. Negative. At negative 1, 2, this is the point, right? We should have a negative slope there. So go ahead and give that a shot. Alright, so... Christian, what'd you come up with? -2. I think that sounds good to me. Okay, so let's see here. Run through this work here real quick. So the setup here is the limit as delta x approaches 0 of f of, well, our x value here is -1 that we want to approach, plus delta x minus f of -1. Okay, so here, because it's not 0, we can't like simplify that at all, so we have to like just kind of basically, plug that whole thing in. So let's see here, -1 plus delta x goes in there, so it's -1 plus delta x quantity squared. Don't forget the little plus 1 there too, that's part of f. So it's -1 plus delta x squared plus 1 minus, and then f of -1. So let's see, -1 squared is 1, plus 1 is 2. All over delta x there. Now, -1 plus delta x, to square that, what do we have to do? I'm going to FOIL it out, right? Okay, this is a binomial, so it's going to be, let's see here, positive 1 minus 2 delta x plus delta x squared. When you simplify that, plus 1 minus 2, excuse me, all over delta x. Okay? And what cancels out of this numerator?
All the content.
So yeah, 1 plus 1 is 2, minus the 2 though gives us a 0, and so I'm left with -2 delta x plus delta x squared all over delta x. And then what can we do to continue simplifying here? Factor out of delta x, exactly. So the delta x's cancel, and I'm left with the limit as delta x approaches 0 of negative 2 plus delta x, which therefore is just what? Now we can finally do the direct substitution, and we get negative 2. Wow. Okay? Negative 2 is our slope there. Okay? Pretty crazy. Questions on any of that? So you can see now why we harp on you so much about doing this accurately. There's a lot of work involved, but once you simplify it down, you get that nice answer there, negative 2. Okay, this is why we work on this, because this is not easy substitution. This is not easy work and manipulation there, but you get that nice little answer there. Any questions on that? Any questions? Okay. All right. So, flip over your paper, please, and we'll look through this. So this slope of the tangent line stuff, all that, okay, the limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus, and that is differentiation, okay, or that's the process of finding the derivative, okay, process of finding the derivative. So we're expanding our vocabulary here. We're going to start using, these fun mathematical words. Okay. So the definition of the derivative of a function. Okay. So the derivative of a function. The derivative of f at x is given by. Now notice here the new notation that we're seeing show up. What's new in here? Yes, this little apostrophe, we call it prime, okay? If you guys remember from geometry, when you transformed shapes, right? If you took a point A and you translated it, slid it, or you rotated it, or you reflected it, the new thing was called A prime. It was transformed. So here, our function f, right, is being transformed. We're taking the derivative of it, and so this indicates f prime of x. This means the derivative of f at x. And how do we find it? We use it, this is one way we do it, using the limit definition of the derivative. Okay? Of course, provided the limit exists. This is key. Okay? All the ones that we did, the limit exists. Sometimes, though, the limit won't exist, and so you can't find the derivative at that particular point. Okay? There are places, believe it or not, right, where the limit will not exist, or the limit definition will not exist, and therefore you can't find the derivative at that point. Okay? It will be called not differentiable. Okay? Not able to be differentiated, right? Not differentiable. The process of finding the derivative of a function is called differentiation. Oh, well, okay, I guess it's already there, so we have it twice now. Great. A function is differentiable, right? Able to be differentiated at x if its derivative exists at x. Okay, kind of duh. And differentiable on an open interval, a, b, if it is differentiable at every point in that interval. Okay? So, now, next thing, also very big, new stuff here. So I know this is a lot to throw at you, but new notation. So there's other ways to mean the derivative besides just that f prime that we saw up here. Okay, so notation is used to denote the derivative of y equals f of x. Okay, so we saw this one, f prime of x. Number 2 here, dy over dx. Okay, and there's more read about that here. You can see the notation dy over dx is read as the derivative of y with respect to x. Okay, and you may be like, why do we have this? Where is this even coming from? Well, when we take the derivative of a function, right, f, that's the derivative of the function with respect to x. We take the derivative with respect to the variable x here, so that's why f prime of x. But sometimes functions, right, instead of f of x equals something, sometimes you just have y equals something. And so that's how you show that derivative there, dy dx. Or the derivative of y with respect to x. And then y prime, you could also use y prime instead, also the same thing. And then here's another way to write it too, and this is the derivative of f of x with respect to x. Okay, so the d stands for derivative of f of x with respect to x. Okay, yes.
So are these all used interchangeably, or is that specific situations in which they apply?
So they're kind of used interchangeably, but they also naturally flow from certain problems. So for example, let's say I wanted you to find the derivative of y equals 3x plus 2, like we did before. then the notation you would use for the derivative, you would use either y prime or you would use the dy dx. That's the typical way you'd
So
see
it's
it
relative to
because you
that.
start with the y. However, if I started with f of x equals 3x plus 2, then your typical notation to indicate the derivative would be f prime of x equals, dot, dot, dot. Or sometimes the way you see this is more like as a problem. You'll say, okay, number 17, we would like you to find the derivative with respect to x of the function 3x plus 2. And then you would go about and find the derivative of that function. So this is more indicating like an operation, to do this thing. This is kind of saying, here's f, what is the answer, and here's y, what is the derivative, what is the
So
derivative.
it's relative to the...
It's relative to kind of the question, yeah. And you'll get more of a sense of that as it goes, but that's the basic idea. If it starts with y's, then use the y prime and the dy dx. If it starts with f, then use the f prime, so on and so forth. All right, we're going to look at two more problems here, and the one's here and then one's on the other page, but, okay. And so we're going to look here at this function. So the square root of x. All right, kind of fun. Now, in the previous problem, let me go back here. In the previous problem, well, actually, let me read through this first. So find the derivative of f of x equal to the square root of x. Then find the slope of the graph of f at the points 1, 1, and 4, 2. Discuss the behavior of f at 0, 0. So, the point 0, 0. Yeah. So, a good question, though. Yeah, exactly. It wasn't very clear there. But when it says, like, at a particular point, it would be, at means kind of a particular point, not an interval. But back to this. So now here, this is slightly different than the one that we just did. Example 2, the directions were find the slopes of the tangent lines to the graph of f of x equals x squared plus 1 at these 2 points. And we did 2 separate pieces of work here. We had to do 2 different limits. But actually, we can find, here it says, first find the derivative of f of x for f of x equal to square root of x, then find the slope. So what that means is we're actually going to find the derivative, the limit definition of the derivative of this generically, then we're going to plug in the points and find their slopes. Okay? So we're going to find like a generic formula for the derivative of this, a general formula for the derivative of this, and then use that formula to plug in these points and find the slopes. So rather than doing 2 limits to find the slope at these 2 points, we're going to find just 1 limit and then use that general limit to plug in here. So let me show you what I mean by that. Okay? So, we're going to take the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. By using the x's here, we're going to come up with a generic formula for the derivative. Okay? We're not going to find the derivative at a specific point. We're going to come up with just a generic formula for this derivative. Okay? So our function here is f of x equals the square root of x. So then let's start simplifying this. So if I want to find f of x plus delta x, what would I write then?
Square root
of x plus delta x. Right? If I want to find f of Bob, it would be the square root of Bob. So if I want f of x plus delta x, I need to do square root of x plus delta x. Minus then, what's f of x?
Square root of x.
Square root of x, right? All over delta x. Now you might look at this and say, Mr. Whitmire, great job. We don't have any numbers in here, and now it's impossible to simplify this thing. Right? Or is it? What do we do when we see these square roots? What's one option that we have? Multiply by the conjugate. So we're going to multiply this by the square root of x plus delta x plus root x over the square root of x plus delta x. Oh boy.
This one is fun.
Yes, there's like no numbers. How fun is that? Oh my gosh, I'm really like, hang on a second, I gotta get my whiteout pen. This is... Let me fix this, because this is a hot mess right now.
Is that like a ballpoint pen?
It's like a ballpoint whiteout pen, yeah.
Wow, it's like it's not even there.
Okay. It is on video, but I fixed it, so I'll just edit that part out, so... Oh, yeah. So anyway, so there it is. So now, we get the joy of multiplying this out.
That's actually fun. That's so satisfying.
It's not too bad, though, because the middle terms we know are going to cancel. So, you know, we can kind of take advantage of that fact. So it's just going to be the first two terms squared. So what's root x plus delta x times root x plus delta x? Yeah, it's just x plus delta x. And then minus, what's root x times root x? X, right? And we know the middle term's going to cancel, right? We have a positive root x plus delta x times positive root x, and then a negative root x times root x plus delta x. So those middle terms are going to cancel. And then in the denominator, do not, by the way, you know, distribute this. It's not necessary. It's just going to cause you more work. Okay? All right, great. We've multiplied by the conjugate. Now what?
Simplify.
No, can't substitute just yet. If we substitute now, we'll still get 0 over 0. Simplify. Yeah, the x's cancel, don't they? X minus x.
And then the delta x.
And then, yeah, I'm going to rewrite it just because I'm a masochist and I like to cause myself more harm. So here we go. All right. Okay. And now, right, what else cancels? The delta x's. So what's left in my numerator then? A 1 over the square root of x plus delta x minus the square root of x. Whew. Oh my gosh. All right. It's still pretty ugly. Oh, plus. Sorry. Thank you. Plus. Still pretty ugly. What can we still do, though? Now we can finally plug in a 0 for our delta x. And so we're left with 1 over square root of x plus the square root of x, which is the same thing as 1 over 2 square root of x, right? 1 square root of x plus 1 square root of x leaves us with 2 square roots of x. Wow. Wow. All that mess. And that is the derivative. Sorry, that's the derivative. So this thing, this is f prime of x equals 1 over 2 times the square root of x. That's our derivative. Now, why is that useful? How did that help us?
Now you can just plug in your numbers.
Because now you can just plug in the numbers. Exactly right. So if I want to find the slope of the graph of f at the points 1, 1, what do I need to find? F prime of what? 1. So what is f prime of 1? Well, let's see here. It's 1 over 2 times the square root of 1. So what is it? 1/2.
Take a picture of this and send it to Quinn and Ethan and be like, I did it.
Yeah, that's right. I'm calculusing.
I can do it, guys.
Yes. Eventually.
That's an easy way, what?
Eventually. Okay. No, I know. Spoiler alert, right? But no, it's okay. And then the slope at x equals 4. Okay, so that's going to be f prime of 4, right? And so let's plug in 4. So it's 1 over 2 times the square root of 4. So square root of 4 is 2. 1 over 2 times 2 is 1/4. Wow. Cool. So easy. Now, what about, it says to discuss the behavior of f at 0, 0. Well, let's try it here. What is the slope at x equals 0? And yes, f prime of 0, it's undefined. You get 1 over 0. Huh. I wonder why. Well, let's look at the graph. Let's graph it over here. Oh, question?
Oh, no.
Oh, you have an answer?
I just like make no. I was just,
Why does it make sense?
because that's just like a point. Like you could take the. If you took a 1, that's like I can't explain. I can just see it in my head. Just say
Okay.
it that way.
Let's
There's like
graph.
an infinite amount of like ways.
Right,
to, like,
okay, I see what you're saying. Yep. And that's it. You're right, it's hard to describe, but you've got the idea. So let's graph square root of x. So let's plug in 0. Square root of 0 is 0, so we get the point 0, 0. And then at square root of, let's see, at x equals 1, square root of 1 is 1, so it's 1, 1. And then 2, I don't really know what root 2 is, or root 3, but root 4 we know is what? 2. And then root 5, root 6, root 7, root 8, root 9 we know is 3.
Oh, you went for the one-liner.
I did. I feel pretty good about it. I feel pretty good about it.
Stand up, you have to get the right angle.
That's right. I was just like, I gotta be real careful here. Focus. Got it. Nailed it. Okay. So anyway, so let's look at this. the slope of the slope of f at x equals 1. So there's x equals 1. Do we believe that's a slope of maybe about a half? Up 1, right 2? Yeah,
Sure.
you know, it's about right, yeah. And what about at 4? 1, 2, 3, 4. It's a slope of 1/4. So here's something, right? 1/2, is that steeper or less steep than 1/4? Steeper, right? And do we kind of believe that, right? As we go with our curve here, our curve is kind of flattening out, right? And so this should be a steeper curve than that one. So 1/2 will be steeper than 1/4. That looks good. And then at 0, though, right? The slope is kind of like, it's kind of, you know, getting steeper, but as you get to 0, well, kind of like there's no other left-hand side here, right? And so the slope just kind of doesn't exist, right? So the slope there at 0 is undefined. The derivative does not exist at 0. Now, here's something else. Here's another way we can kind of convince ourselves that the slope at 0 does not exist, okay? What do we use to find the derivative? A limit as delta x approaches 0. For a limit to exist, the left-hand side and the right-hand side must be what? Must be approaching the same thing, must agree.
F exists in the first place.
Does the right-hand limit exist here?
Yeah.
Yes. Does the left-hand limit as x approaches 0 exist?
No.
No. Okay? And so at 0, the derivative cannot exist because the left-hand, right-hand limit don't exist there. Okay? Don't agree. Okay? So that's no good. No bueno. Okay? So the derivative does not exist there. And there are other situations, too, where the derivative will not exist. But we'll look at those later. Okay. So, I don't have a piece of paper for this for you guys, so you're going to want to just get out your own sheet of paper. We're going to do one more. Uno más.
We should do a whole entire calculus
No más?
class in Spanish.
I can't do that.
I would walk
Oh,
out.
there you go.
I wouldn't be able to do it.
We could do it all. Nous pouvons le faire tout en français.
I feel like
to me-
in like the Enlightenment and stuff like that. I feel like mathematics was written in French. I feel
I don't
it was
like
kind of
like
the-
how French sounds.
French sounds
I
so
hate
nice.
how French sounds.
What are you talking
I
about?
hate how it sounds.
It sounds better than Spanish. Must be really
I hate how Spanish sounds too. I like German. I like German and Russian and
Why, it sounds
English.
angry and sounds just like this jumbled.
Yeah, it just sounds
Like,
like.
yes.
Yeah. It just
Like a
sounds
weird
so
noise.
like German every time. It's just like punching someone.
French sounds are culture.
No, French sounds awful.
Sounds amazing. What do you think, Mr. Webb?
I think actually all those languages can sound beautiful depending on who's speaking, how they say it and stuff.
I think
Even Russian and German, I think, definitely can sound. I'm not that they're normally harsher languages, but they can still sound beautiful too. But I also think French and all that shit. Right, probably, yeah. What they're known for, right?
We're saying that Hitler screamed.
Yeah, Germany. Yeah, that's right.
Okay, so
He's like,
here's this one, right? Okay, so we want to find the derivative with respect to t. Now, why t? Well, t is now our independent variable. Okay, we'll look later about what that whole with respect to, variable, like the whole with respect to, like what that means exactly. But in general, in calculus, we're going to be taking the derivative with respect to our independent variable, right? Like the thing that's on the other side of the equal sign from like the y, basically, or whatever we have. Okay. How we've defined it. All right, so let's give this a shot. So let's set this up. So again, we don't have a specific point. We're not trying to find a specific slope at a specific point right now. We're just asked to find the general derivative, right? There's no like find the slope of y at the point t equals 3. So we're going to just find the generic derivative. So that means we're going to use the limit. And you can still use delta x if you want to. Delta x approaches 0.
Could we also set y prime?
You could write, you could find just like y prime and stuff like that. Yep. So, the limit is delta x approaches 0 of f, and I'm going to put a t in there plus delta x minus f of t all over delta x. And I know this is not f of t, Mr. Whitmire, it's y. But we could write that. I mean, it's still the same thing to say f of t equals 2 over t, right? Same idea. And because it's the way we have our, our limit definition set up, that's why I'm writing the f of t plus delta x. Okay. Okay, so this is equal to then the limit as delta x approaches 0. Okay, f of t plus delta x. How are we going to write that? 2 over t plus delta x, right? Minus f of t is just 2 over t. All over delta x. Fractions within fractions within fractions. It's like fractionception. Yeah, that's right. Nested fractions. Okay. So, we could try plugging in 0 for delta x here, but you can probably guess what we're going to get. 0 over 0, right? We got to simplify first. So what do? We have fractions within fractions. What's our general strategy we go for? Common denominator. All right. So what's going to be? What do I have to multiply this first fraction by? Yeah, t over t. And this second fraction, I got to multiply it by t plus delta x over t plus delta x. Okay? Ugh, this is yucky, Mr. Whitmire. Yes, some of these problems can take up a whole half a page. Whole half. Anyway, alright. Let's see. 2t minus the quantity 2 times t plus delta x.
No.
All over t times t plus delta x. All over delta x. I'm sorry. Just a skosh. Scooch it a skosh. Yes, you're welcome. Okay, so I kind of did 2 steps at once here. I got the common denominator, and then I went ahead and put these 2 things together in the numerator. Okay, so 2t, and then minus 2 times t plus delta x on the other side there. Make sure you have, when you do that subtraction, right, this subtraction here distributes, right? So that's why I put the parentheses around that quantity there. It's going to distribute. Be very careful, guys. I know this is so difficult. I mean, this really is. I'm not going to, sugarcoat this. I make it look real easy because I've been doing it, forever. But, I mean, I know it's tough for you guys. It's so hard because you lose one little minus sign somewhere and everything is gone now. Everything's messed up. The good news is this is not what we're going to do for half of calculus, okay? Maya is correct. There is a shortcut we're going to learn, but I want to make sure you guys got it this way first. Because I hate you, yes. So, 2t minus 2t minus 2 delta x. 2t.
Okay.
Okay?
I still got this one.
So the 2 t's cancel, right? And so we're left with negative 2 delta x over t times t plus delta x all over delta x. Okay. We still have fractions within fractions, though. But now that we have our numerator that was 2 separate fractions, now that's one fraction, what can we now do? Instead of dividing by delta x, we can change that to multiplying by 1 over delta x. So it's negative 2 delta x over t times t plus delta x times 1 over delta x. Okay, and now that we have this, what cancels?
Oh,
sorry, I'm off the side
delta
there.
X does.
The delta x's cancel. We get negative 2 over t times t plus delta x. And now finally, we can plug in 0 for delta x. We get negative 2 over t squared.
Nice. That was fun.
All that mess about 5 minutes ago. We will learn the shortcut, I promise, but I want you to know it this way first. Okay? So there's the derivative. Yay! So we can say, what can we say? We can say y prime equals negative 2 over t.
Wow, I should have paid
Ooh,
that
shoot.
closer.
So what can we say? We can say y prime equals negative 2 over t squared. Okay, that's one way to write the answer. We could write dy, not dx, dt, because we took the derivative of y with respect to t. Dy dt equals negative 2 over t squared. That's another way to write it. I could write f prime of t equals negative 2 over t squared. That means the same thing. Right? Or I could say that the d dt of f of t equals also negative 2 over t squared. Right? So 4 different ways to write that. What would be the primary ways you'd write it? Either the first one or the second one. Those two would be the most likely ways that you would write it out as your answer, because it starts with y equals, and so you would end with the y prime equals, or the dy dt equals. Okay? Questions on that? I'll zoom out so you can see the whole thing. Okay, great. So let's now use that information. Let's not waste it, right? We did all that work. Let's actually use it for something. So let's answer, for part B here, let's answer the question here. What is the equation of the tangent line to y at the point 1, 2? Okay.
Yeah,
I'm sorry. Yeah, T-O-Y. What is the equation of the tangent line to y at 1, 2? To y at 1, 2. Towards y at 1, 2. Okay? Well, let's just think about this. What do we need to write the equation of a line? We need a slope, and we need a point that's on the line. Well, do we have a point that's on the line? 1, 2. Yeah, it's going to be on our function, right? This point is on our function, but it's also going to be where our tangent line intersects our function, because this is what we want to be, the tangent point, the point of tangency. So that's our point. How can we find the slope of our tangent line? Use the derivative, right? That's what the derivative is. The derivative is the slope of the tangent line. So we're going to evaluate here. Now, what do I plug in? Which one of these two do I plug in for t? The x or the t value, right? The 1 is what goes in. The 2 we're not going to use. We just need to worry about the derivative here. Only depends. The value of the derivative only depends on the t value. So it's just going to be negative 2 over 1 squared. So equals negative 2. Okay, if you want to write this kind of in a very official, like mathematical sense, you could put y prime evaluated at t equals 1. Whoops, 1. Okay, so y prime, this vertical line, and then a little like sub t equals 1 there. That means y prime evaluated at t equals 1. Do you have to write that on like tests and stuff like that? No, but it just is like that's the official like. Yes.
Would they
Absolutely.
write that like that on the AP test?
You can see it in a question, yeah.
stapler?
Oh, stapler is probably back on my desk. So, there's my slope. Great. So, how do I write the equation of a line?
You take the original.
Y minus 2 equals negative 2, parentheses. And you can see now why I wanted you guys to learn point-slope form, because we're done. We don't need to find a y-intercept. The work is done for us. There it is. That's the equation of our tangent line. Okay? Now, I want you all to get your graphing calculators out, because we're going to actually see that this is true. Okay, does anyone not have a graphing calculator?
How did you go from the left to the right?
That's our slope.
Yeah.
That's our point. So for point-slope form, we have all we need.
Okay.
Okay, so y1, we're going to graph 2 over t, the original function. So 2 divided by, well, x in our case, because you know. Okay, I'm going to be a little bit lazy here and not put parentheses around my numerator and denominator because there's only one thing in the numerator and one thing in the denominator, so you're safe. You should be radian mode. Okay, yeah, make sure if you guys are if you're in physics, if you're in physics, make sure you're switching back and forth because in this class, we want to have radians. Calculus commandment, thou shalt always calculate in radians, unless the problem's in degrees in the first place. Okay, now, we're going to graph this. Now, this is not quite in the normal format, but what's the only thing we have to do to solve it for y? Add 2 to the other side. So it's going to be negative 2, parentheses, x minus 1, plus 2, like that. Right?
Sure.
Now, graph it.
Oh, that looks very nice.
Boom. Look at that. Looks pretty tangent to me. Looks pretty tangent to me, right? Touches the graph at one spot, just comes in and kisses it right there. Now, we can even check to see that it intersects. At what point, at what coordinate should these two things intersect?
1, 2.
1, 2, because that's the point of tangency, right? That's the equation. So let's check. So second, trace. Go down to intersect. Make sure that your little cursor is on the right curve there, and then it goes to the second curve. And then the guess, you just want to move your cursor so that it's close to the point of intersection. And it's working, and it's working.
Mine says,
oh my gosh, don't fail.
Mine says error iterations.
Okay, it might be because of the way the graph looks. Hang on, let me try something else. All right. We might have to change our window here. So let me go to window, or sorry, let's do zoom, and we'll do zoom box. Let's zoom in on the area using zoom box, maybe. I think that's what the issue is.
Or you could just go to your table and do that Y.
Zoom and then zoom box. And then we'll zoom in on that area. And now I bet if we do intersect, it'll work. Oh gosh. It's not going to work. Yes, it did!
I was going to say you go to the table and just plug in Y.
You could also, yeah, that's true. You could just go to the table. That's true. I didn't think about that. Okay, so I zoomed in on my point of intersection and then did the intersection command. And you can see here, the calculator, right, there's some clear error here in the calculator's calculation. But we can see x is definitely going to be 1 and y is definitely a 2 there. Okay, so they definitely intersect at 1, 2, and it looks tangent. Okay.
Go to the table.
You can also go to the table, yeah, second graph, and if you type in the point 1 for your x, then you see that both the y1 and y2 give you a coordinate of 2, so therefore they do intersect at, 1, 2. Okay, so wow, it works. The math holds up.
Math works.
Okay, alright, I want to show you one more thing, and we'll do one more example, and that's it. So thank you guys for bearing with me. It's a little bit intense today, but
Oh, you're good, Mr. Wood. You're good.
I'm good, thank you. Okay, I'm going to show you an alternative definition, an alternative limit form of the derivative. Is, okay, this. F prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. Okay, again, that's if the limit exists. This is not what we have been doing. It's close to it, but it's not exactly what we've been doing. It's kind of, oh, sorry, I didn't hear you say kind of. Sorry, I thought you said, isn't that what we've been doing? That's what I thought you said. It is kind of like what we've been doing, yes. Yes, I apologize. Okay? But let me indicate what is, so let me kind of show you here. What's different? Notice for this specific form of the derivative, we're finding f prime of c. So this form we cannot use to find a generic derivative. Okay, so what do I mean by generic derivative? This negative 2 over t squared was a generic derivative, right? It's just like the general derivative of our original function. This, though, you can only use this form of the derivative to find the derivative value at a point. See, you can see it's f prime of c. That means we need to be finding the derivative at a point. Okay, and in this case, it's whatever the c value is.
So if it tells us to, like, find a derivative...
If it tells you to find the derivative of a function... Exactly. If it tells you just find the derivative of f, that means you have to use the old limit definition. But if it says find the derivative of f at 3, then you could use this one or the old one. Either one works.
No, this one's easier.
Okay? But you do need to be familiar with both. Okay? Let me repeat that. You need to be familiar with both. So that's why I'm going to show you this one as well. Okay? Let me highlight this. The existence, okay, of the limit in this alternate form requires that, and then I'll put it in parentheses here. Well, if it's a limit, right, the left-hand limit and the right-hand limit need to be equal. So the limit as x approaches c from the right of f of x minus f of c over x minus c needs to equal the limit as x approaches c from the left of f of x minus f of c over x minus c. Right? Which is like not that mind-blowing of a concept, right? It's just something you have to keep an eye out for. The left-hand limit and the right-hand limit of that derivative definition there need to be the same. And they should be equal. Okay? And then I'll show you one example using this alternate definition. Okay? And we're actually going to take this from before. So any questions so far? Any questions so far? So again, you need to be familiar with this second method. Most 90% of the time, we're going to use that first method, but you also need to be familiar with this. Not only because it could show up on a test, but it could show up on the AP test as well. Sometimes they set it up using the first form, but every once in a while they'll set up a problem using this form, and so you just need to recognize it. Okay? All right. So let's do one quick example here of how this works. So this is from before. Okay, we're going to find the slope. Oh my goodness. Find the slope of the tangent line, which you know is synonymous with finding the value of the derivative of f, right? Find the slope of the tangent line to the graph of f of x equals x squared plus 1 at negative 1, 2. So remember, we just done this one, right? We've just done this one. We already know the answer should be negative 2, because that's what we got. Okay, but let's do it now using this alternate form of the derivative. So, what is our c in this problem? What's our x value that we are trying to find the value of the derivative at? So yeah, our x value here, negative 1. We want to find the derivative for the x value of negative 1. So that means we want to take the limit. So we're basically trying to find f prime of negative 1. So that means it's going to be the limit as, this is again the alternative form. If we were using the first form, we'd write the limit as delta x approaches 0. But here for this form, it's the limit as x approaches negative 1. Okay, in this particular form, our limit approaches whatever our x value is that we're trying to find the derivative, okay, of where we're trying to find the derivative. So it's slightly different, okay? The original one that we learned, it's always limit delta x approaches 0. And this one, though, what we're approaching changes based on the value of the derivative we're trying to find. Okay, so it's then going to be f of x minus f of c. But what's f of c? Well, c is, again, negative 1. Okay, all over x minus c, so x minus negative 1. Okay? So you can see it's slightly different. But let's see what happens when we simplify here. All right, so we haven't evaluated the limit yet. So we'll write limit as x approaches negative 1. Right, if I were to plug in negative 1 right away and try direct substitution, what would I end up with? 0 over 0, so that's no good. Okay, so we have to do some work here. So what is f of x? X squared plus 1, the function, right, minus f of negative 1. Well, let's see here. Negative 1 squared is 1, plus 1 is 2, so it's minus 2, all over x minus negative 1 is really what? X plus 1. Woohoo! Alright, now we can simplify the numerator, right? 1 minus 2 is negative 1, so it's x squared minus 1 over x plus 1. Okay, great, so we simplified, and now if I direct substitute, let's see, I get negative 1 squared is 1, 1 minus 1 is 0, over, oh crap, it's 0 over 0 still.
Factor.
Right, we can factor though. X minus 1, x plus 1, over x plus 1, and then what happens?
Cancel,
X plus 1's cancel, baby. And so we're left with the limit as x approaches negative 1 of x minus 1. Whew. And so now what can we finally do?
Congratulations.
Direct substitute, and we get negative 1 minus 1, which is negative 2. Wow.
I just said that up a stupid or
Way to go, everyone. We got the same answer as we did before. Which is good.
Look at
Okay.
all that work.
Oh, I have.
It's just like so satisfying to just like write out every single thing. Yes, it is.
I agree. I think it's like, it's very,
so satisfying.
it's
to do all
meticulous,
that,
and
at
yeah,
the
yeah, and then you get that
end,
nice little answer, and you're like,
Satisfying to get the answer, but not satisfying to write.
All right, one
Okay.
one over 1. All right.
Any questions?
Negative 2 over 1. All right. Negative 2 divided by 1.
Okay, so that's it for the notes. Let me then give you guys your assignment. Okay, so let me cut the tape here.